Welcome back. Optimization continued. All right, now we're going to tackle a couple problems, especially this first one I really like. I don't really know why, but I sort of enjoy the problem, and that calculus can help us figure it out. So here's the question. Find the largest rectangle that can be inscribed between the sine curve and the x-axis. All right, so this is something we should think very carefully about understanding what's going on here, and I think we should go straight to a picture of what's happening. So let's sketch it out, at least a little bit. So let's take, and we'll go, so we want, so it's between the sine curve and the x-axis. Hopefully it makes sense that every piece of the sine curve is the same size. So let's just take the first part of the sine curve. So go something like this. So here would be our x and our y axis. All right, and so sine starts off here at 0, 0, goes up like this, comes back down. We should probably label this point. Hopefully you know that that is pi. If you didn't know, it is pi. That's the first wave, first arch of the sine curve, okay? Now what we're going to do is sketch a rectangle inside of it. That's what we mean by inscribe. And we want to figure out what are the dimensions of the largest rectangle that can be inscribed in the sine curve, okay? So there's kind of a picture of what we've got going on. All right, now we need to institute some variables here. We do know that this point is pi, but the distance from the x-axis where the rectangle starts, in other words, this distance here is unknown, right? And it's going to vary. And so we're going to call that x. And I think that makes sense because if this was at 1, let's say, then I would say, well, where on the coordinate plane is that point? And you'd be like, well, it's at 1. And it'd be like, x equals 1? You'd be like, yeah. Okay, so I think calling this x makes sense for that reason because it fits in with the xy axis. You can call it n if you want, but it seems less helpful if we do that. All right, you call it n or something else if you want, but it doesn't seem as helpful. Okay, so if this distance is x, the only way that this is going to be a rectangle is if this distance right here is the same. Otherwise, it wouldn't be a rectangle. I know I've got a bad picture, but you get the idea here. Okay, so your picture is probably better. But anyway, the gap here and here has to be the same. Otherwise, it won't be a rectangle. So if that's the case, then we can get one dimension. We can get the length of our rectangle, at least abstractly. We know the whole thing here is pi. So taking off these two pieces, we will get this for the length of our rectangle. Pi minus 2x. Okay? Now, let's take and find the other dimension, which is the height of our rectangle. Okay? The height of our rectangle is going to be based on the function value at whatever x is. Okay? To find the height, what we'll do is we'll take and well, first of all, let's identify this point. This point right here, where the rectangle intersects the sine wave, would be x, comma, sine of x, right? If you plug in 1, the height here would be sine of 1, right? Same idea over here. Excuse me. Except we don't really need to label that. That is, this is pi minus x, comma, sine of pi minus x. Okay, so at this point, we can figure out what the area of the rectangle will be. It is length times width, right? And so let's write that out. So length is, or length times height, I guess. Length is pi minus 2x. And then the height is going to be sine. Okay, let's take the derivative of that real quick. Product rule problem. So it'll be first, which is pi minus 2x, times the derivative of the second, which is cosine x, plus the second, which is sine, times negative 2. Okay, so there's our derivative. And it turns out that we're actually going to have to go to the calculator on this because what we want to know is when is this function 0? What are the critical points of it? And so we'll have to graph it to solve that. And so it turns out that a prime is 0 when x is 0.7105, when x is 0.7105, okay? And so the height is just going to be, well, I guess I can write this out. So the height will be the sine of 0.7105, which turns out to be approximately 0.65. And then the width, or length, I guess I've been calling it, but the width here is going to be pi minus 2 times 0.7105, and that'll be equal to 1.72. This is another one where we've got to be careful what they're asking. We're trying to find the largest rectangle, and actually it should have been a little bit more clear, but we're looking for the dimensions of the rectangle, not the x value. It's very easy to get the x value, pat yourself on the back and move on, but we are looking for the dimensions. Sometimes they'll ask you for the area. That's a little bit easier to find because we can get that from the original function, but that's how you do the sine wave inscribing problem. Okay, let's go on to the can problem. Here's our goal in the can problem. We are trying to minimize the material used to create a cylindrical can that is 1,000 cubic centimeters. Okay, so we're trying to build this can, and hopefully it makes sense that we can vary the height of the can. We can constrain the volume to 1,000, but there's lots of different combinations of radius and height of the can that we would use, and some of those will use more material than others. Some of those dimensions will use more material than others. So we want to figure out what is the best height and radius of the can, or diameter of the can, that gets us 1,000 cubic centimeters but uses the least amount of material. Okay, so ultimately our goal then will be an equation for surface area. If we can minimize surface area, we're minimizing materials. So we're taking a second to understand the problem and thinking ahead. I need ultimately an equation for surface area. Let's sketch the situation out first. So I'm just going to sketch a cylinder here. We don't know. Good cylinder, Cresswell. All right, let's assume it actually was a cylinder, all right? And we don't know what the optimum radius is, so we're going to put that in as R. And we don't know what the optimum height is, so we're going to label this side here H, okay? And then let's come up with, well, actually, we need two equations ultimately, but let's start with that surface area equation. What is the surface area of this going to be? So surface area. What this will be is the top and the bottom, and so that'll be two things, and let's just write that down. That's pi r squared is the area of a circle, and we need two of those, so 2 pi r squared, okay, plus the side. Okay, so if you were to take this cylinder and you were to cut it and unroll it, if you were to cut it and unroll it, you would get this. The side length would be h, right? And then the length of this rectangle, the unrolled part of the can, would be equivalent to the circumference of the circle. So it would be 2 pi r. All right, so what we'll end up adding then is 2 pi r times h. That gives us the surface area, all of the material, okay, used in the can. We're also going to use this is, again, a situation where we're trying to optimize surface area. We have two variables. We need another equation to help us out. So I'm going to take and use volume as my other equation. Volume is going to be equal to pi r squared h, the area of the base, which is pi r squared, times the height. So pi r squared h. Okay, and I'm going to use that to eliminate one of the variables over here. It's going to be easier to eliminate h than r because r shows up in two spots. So we are going to solve this equation on the right for h. So h is going to be equal to 1,000 divided by pi r squared. So we're going to drop this in here. Okay, so this is what I get. Surface area is equal to 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. And then we're going to simplify. We're going to try to go full out non-calculator here. until the very, very end. And I'll show you we can actually leave our answer without using our calculator if it was asked of us. So 2 pi r squared is not going to change. 2 pi r over pi r squared, we're going to have an r simplified to 1. One of the r's in the denominator is going to cancel out. Pi over pi is just 1. So I'll be left with 2 times 1,000, which is 2,000, divided by r. Okay? Now, if I want to solve this for, ultimately set this equal to 0 and so, sorry, back up. If I want to take the derivative of this, then what I'm going to do is rewrite this as 2 pi r squared plus 2,000 times r to the negative 1. And then I'm going to take the derivative. So surface area prime, probably the book uses just s instead of sa, and I probably should have too, but the derivative here is going to be 4 pi r plus, minus, when I put the negative 1 out in front, it'll be minus 2,000. Subtract 1 from the power, r to the negative 2. Okay. Set that equal to 0. So I get 4 pi r minus, and this is ultimately, in its nicer form, 2,000 over r squared. I'm going to add the 2,000 r squared to the left, so I get this, 2,000 over r squared. It's equal to 4 pi r. And then I'm going to times both sides by r squared. So I get 1 over here times 1,000. Over here I get 4 pi r cubed. Divide both sides by 4 pi, so I get r cubed is equal to 2,000 over 4 pi. Cube root both sides. And I get this, r equals the cubed root. And the 2,000 over 4 is 500, right? So I get 500 over pi. Okay, so there's my answer. If I can't use my calculator at all, is the cube root of 500 over pi. If I can, that turns out to be r as 5.42 centimeters. And then, so that's our radius. And then our height would be, if we plug in r right here, we can get our height. And so it turns out that the height has to be 10.84. If you look at those numbers, there's an interesting relationship between them. The height is double the radius. And it turns out that if you want to optimize, if you want to minimize the amount of material used in a cylindrical can, or just minimize the surface area of a cylinder, the optimum ratio of radius to height is the radius being half the height. Will give you the optimum surface area given a constrained volume. And I think that finally wraps up the section 4 lessons. A lot of this section, a lot of doing well in this section is working on these problems, really trying hard to tackle each one, and then also working with your peers as well. So we will try to use small groups in class as much as possible and make sure that you're getting help from me as well as much as possible. Just there's no way to get better at these except to practice them and force yourself to grapple with the problems. It's an unfortunate thing, but it's the it just takes work, and the more of them you do, the more comfortable you get with them, the quicker you will see the relationships that you need to solve the problems, and the easier they will get.